So now that we have that overview under our belt, we're ready to begin to get into various sorts of pitfalls and errors we can have when we make a hypothesis test, when we do hypothesis tests. One of the things that you have to do is you have to make sure that you're aware of what type of test you're running. And this is a really basic mistake, and it's a really kind of fatal flaw, because if you make this sort of error, everything else is pretty much wrong. It's important to realize that whenever you're running a hypothesis test, the null is always the same. However, the alternative can change. So for example, if you're testing to see if the population proportion, and here I'll just use an example where we're looking at a hypothesis test on pi, but the exact same thing would apply if I was doing a hypothesis test on mu. There's absolutely no difference, right? So if I wanted to test and see if the population proportion was less than the value under the null hypothesis, okay? Notice a couple of things. First of all, the evidence has to be in favor of the null. Okay, so the sample percentage, notice these are not the same thing. This is a population parameter. This is what I'm testing. And this is my evidence, okay? This is a sample estimate. The data has to be in favor of the alternative. If it wasn't, we would never run the test. Again, it's just like that example with the judge and the Raisin Bran class action lawsuit. You came into court and you're trying to prove the Raisin Bran's putting less than 16 ounces in their boxes, and your evidence says that they're putting in more. Nobody would go to court. The judge would laugh at you, right? I mean, it would be ridiculous. Same thing here. Now, when this happens, when we're testing to see if the parameter is less than the value under the null hypothesis, this is called a lower tail test. And the reason why is if you think about how we're going to compute the p-value, right? So this is the sampling distribution under the null hypothesis. This is the null distribution. This is what pi hats look like if the null is true. Again, our evidence, if we're trying to prove it's less than a specific value, our evidence, our sample estimate has to be below pi naught, and we're computing the area in the left-hand tail or the lower tail. So the probability that this is less than our observed value is this p-value right here, this area right here, hence lower tail test. Okay. And again, how we would do this in Excel, and we're gonna work problems in the next video. We would use norm.dist. Why? Because here we're computing the percentile in the lower tail of a value for some normal distribution. And we know this has a normal distribution by the central limit theorem. This is where this distribution came from. On the other hand, we might be trying to prove that it's different than pi naught. So notice that when you're running a lower tail test, there has to be language indicating. So you're going to be looking for things like, is the population percentage less than? Has it decreased, right? Here, the wording that we're going to be looking for is to see if there's a difference or a change. So here you're going to see wording like less than or decrease. Okay. Here you're going to see wording like we want to see if there's been a change or a difference. Okay. So sometimes, for example, when some sort of change occurs, we don't know how it's going to affect the population. So in this case, notice that our sample statistic, our sample estimator, could be on either side, right? So here, obviously, pi hat cannot be less than pi naught, and of course, it almost never will be. It's very rare, right? This is called a two-tailed test, and the reason why it's called a two-tailed test is wherever the estimator is, say it's here, I'm going to compute the area in a tail and multiply it by 2 to get the p-value. So if my estimator was up here, I'd get the area in this upper tail, and I multiply by 2. And conversely, if my sample estimator was below pi naught, I'd compute the area in this tail and multiply it by 2. And of course, we know how to do this using Excel. Okay. We might be testing to see if the population percentage is greater than a certain value. And in fact, this was the male rat empathy experiment, right? 50% was our pi naught. We had some estimator up here, and we wanted to know how likely is it that if our estimator came from a population of indifferent rats, we could get an estimator this large or larger. Okay? And so here again, our sample estimator has to be above the parameter value under the null hypothesis, and the p-value is the area in the upper tail, hence the word upper tail test. So this is our p-value. Remember, when you're computing areas and upper tails, Excel always gives you the lower tail. It gives you this value, so you have to say 1 minus norm.dist. Okay? So this is the first thing. And again, the way that you're going to determine this is you're going to look at the estimator. The estimator always has to be in favor of the alternative, and you're also going to look for language. So here you're going to be looking for, here you're going to think to change, or you're going to be testing to see if it's less than the value you would believe under the null hypothesis. Here you're testing to see if there's difference. So you're going to be looking for the words like, has there been a change or a difference? And here, of course, you're going to be testing to see if the parameter value increased. So you're going to be looking for words like, increased or greater than, something like that. Because remember, again, these are all going to be word problems, so you're going to have to puzzle through this. Okay, so that's the first thing you have to be careful about. The second thing you have to be careful about is you have to make sure that the conditions for the central limit theorem are met. So you should go back to the book and check and make sure that you know what the conditions for the central limit theorem are, right? So you have to have a random sample, right? It has to be large enough, but not too large. Okay, large enough, that's what this means right here, but not too large. And again, the reason why you need that is in order to compute the p-value, and we need this normal distribution. And saying that the estimators have a normal distribution is only true if the conditions for the central limit theorem are met. If they aren't, and you draw conclusions, if you use the central limit theorem when the conditions aren't met, then your generalization about the population, your conclusion, is not valid. Okay. Okay, one other issue I want to bring up is the standard deviation issue. So one of the things that happens a lot is that we don't know the population standard deviation. And if you don't mind, I'm going to put sigma sub x to emphasize that this is the standard deviation for the variable. We're talking about a quantitative variable now. And the reason why I need to know that is because when I want to use the central limit theorem, I know that the sample mean has a normal distribution. It's centered at the mean under the null hypothesis, and the standard deviation is the standard deviation of the variable divided by the square root of n. And so although it might look a little confusing, it's actually not a bad idea to think of this as the mean of the estimators. And this is the standard deviation of the estimators. And so very often I don't know the population standard deviation for the variable. And the question is, what do I do? And the answer is very simple. We substitute the sample standard deviation. Okay. In other words, I have the sample, I have an estimate for the population standard deviation. That's my sample standard deviation. So we substitute this, and we use it in the central limit theorem. So now we say that mu hat has a normal distribution. It's centered about the mean under the null hypothesis. And now we're going to use the sample standard deviation divided by the square root of n. Okay. We don't have the population standard deviation, so instead we use the estimator, which is the sample standard deviation. And it turns out that this introduces a little bit of a complication, but because we've chose this condition that n has to be greater than 30, it's usually not going to be a problem for us, okay? But there are ways of dealing with the fact that these two are not the same, but we're not going to get into those sorts of details right now. And so one thing I want to do is kind of put everything together. I mean, this course is called The Big Picture of Statistics, okay? And so it's good to see how everything kind of comes together. So, you know, if we think about how the data collection affects inference, this is a really important point. I mean, one of the reasons why I made such a big deal about how you collected the data is that it definitely affects your results. And the problem is, if you do it incorrectly, you won't know how it affects your results. So let's look at the big picture of statistics, right? We pose a question about our parameter, we collect our data, okay? Now, if we have categorical, okay, again, we need random sample, we need to have this sample size condition satisfied, and it also can't be too big. And notice that if these are not met, we can't use the central limit theorem, which means we can't make this huge leap, right, from the sample to the population. Okay? So this is how this all fits together. This is why data collection is so important. If our data collection is not good, we can't use the central limit theorem, and we can't draw valid conclusions. Now, if we switch gears and we look at quantitative, right? Again, we need a random sample because the central limit theorem relies on it. It can't be too big. And we either have to have a normal distribution or we need a sample size of 30, right? And this is one of the reasons why we have to explore and summarize the data, okay? And I'll mention very briefly, although we're not going to get into this complexity, that if the sample is really skewed, you're going to have to use a larger sample size than 30. So even though we're not going to get into these complexities, it's important to understand why we plot the data. We have to look at the shape to figure out if our sample size is large enough. So this question of whether it's large enough very often involves us plotting. And again, if all of these three conditions are not met, we can't use the central limit theorem. We can't draw valid inferences from the sample about the population. So this kind of puts everything together and shows you the big picture of why the data collection is so important to inference. Okay, one thing to remember is that the statistical decision and the conclusion are not the same. Okay, so the statistical decision is our decision on the hypotheses. It's either reject the null or fail to reject. When the p-value is less than alpha, we say the null is too unlikely to occur given the evidence against it, and we reject it. We flip to the other side. When the p-value is, and that should be greater than, my bad. Correct that, please. When the p-value is greater than, we say there's some evidence, but it's not too unlikely to have occurred, and we fail to reject. That's the statistical decision, okay? It's not the same as the conclusion. The conclusion is what you say to a lay person, Okay, so here we don't have any technical knowledge, no technical language. Okay, so we keep the technical language to the minimum. The only thing that we do have to say here that's technical is alpha, or the significance level. Okay, but we don't say anything about hypothesis. So we keep the technical language to a minimum. And this is as if we're communicating our results to a layperson. In other words, a person that's not a statistician. And we're essentially answering the question. So, for example, in the male rat empathy experiment, we would say we find that there is sufficient evidence. This should be is, sorry. There is sufficient evidence to conclude at a significance level of 5% that male rats are empathetic. I've taken the alternative, which is pi is greater than 50%, and I've morphed it into ordinary language. Okay, so two things that change. Change is not to just is, okay, and change the less than to greater. Now, if we had a pi hat, say, of 60% for the male rat empathy, we might have said we find there is not sufficient evidence to conclude at a significance level, or alpha, equal to 5% that male rats are empathetic. Notice the only difference is and is not. Okay, so here we're using the word is, here we're using the word is not. This is exactly the same way that a jury talks in a criminal trial. Right? A jury says that there is sufficient evidence to conclude a person's guilty, or there is not sufficient evidence to conclude a person is guilty. They never say that they're innocent. They're just commenting on whether there was enough evidence to persuade them. The last topic we want to touch on are errors in hypothesis tests. Okay, it's important to understand that whenever you have a conclusion for a hypothesis test, there's always a chance that you're wrong. The only reason why we use hypothesis tests is not because we know on any one particular test if it's true or not, because we don't. It's just that we know how reliable the test is. So in other words, if you kind of think about a little table, if you will, okay? Let's think about a little table here. So this is reality up here. And this is what we decide. Okay? And so if the null is actually true and we decide it's true, there's no error. Okay? However, if the alternative is actually true and we decide the null is true, in other words, something actually happened, but we said it didn't, we made an error. And we call this a type 2 error. Some people call this, in engineering applications or industrial applications, they call this misdetection. Or they sometimes call it a false negative. And this last term is particularly instructive to think about. So it says that it's a negative that's false. In other words, when we decide the null is true, we said nothing happened. So we get a negative, that's what we decide, nothing happened. But it's false. Something actually did happen. Okay. So this is the equivalent of you taking a test for a disease, coming back negative, but you actually have it. Now, let's think about the sort of things that can go on when we decide the alternative is true. So if we decide the alternative is true and it's actually true, there's no error. On the other hand, if we decide the alternative is true, but the null is actually true, we call this a type 1 error. Sometimes in engineering or industrial applications, they call this a false alarm. And in the parlance of medical tests, they call this a false positive. So we have three different terms, okay? This is the statistical term. The type 1 and the type 2 error are the statistical terms. The way most people tend to think about it, though, is in terms of medical testing. In other words, we decided something actually happened, right? It's a positive for our test, but we were wrong. It's false. Nothing did happen. Okay. So if we think about the trial analogy, okay, what would a type 1 error be? Well, a type 1 error would be when we decide the alternative is true, which in this case we decide the person is guilty, but they're not. Right? This would be a type 1 error. It's a false alarm. We said something happened, the person was guilty, but they're not. A type 2 error, it would be a false negative. We said nothing happened, but it did. So here we would decide that the null was true, which is that they're not guilty, but they are. Which is worse? Well, it depends on the consequences, right? In this case, with a criminal trial, it depends on the context of the severity of the crime. If you're talking about a capital punishment case, which is worse, finding a person guilty when they're not, putting an unjustly accused person in jail, or maybe to death, or letting out a person who might kill, more people if they're let to go free. And it really depends. It depends by what metric you're deciding is best, the individual or society, right? So one of the things to kind of think about is the consequences of a type 1 and type 2 error. So let's think about Bardo for a minute, okay? Suppose he's testing his loaves were too light, right? So the null is going to be that they aren't too light, that the average is 16, right? He's testing, remember what we're testing is the alternative, right? So the alternative is that they're too light, or the average weight is less than 16. Now, what would be worse? What is a type 1 error? It's when he decides they're too light, but they're not, right? This is when we decide the loaves are too light. We decide something happened. We decided in favor of the alternative. So we decide that the loaves are too light, but they're not. Okay. So in other words, he's going to overreact. It's a false alarm, right? A type 2 is when they are too light, but we decided they aren't, right? So we decide that they're not too light, but they are. Now, which is worse? It depends. It depends upon the cost of making these errors. Notice that when Bardo decides they're too light but they're not, he's losing money because what does he have to do? The consequences of making this decision is that he has to stop the assembly line and recalibrate it. And so he's losing productivity, right? What are the consequences of a type 2 error? Well, if the loaves are too light, there could be a class action lawsuit against him. And he might end up losing money, or it might become public, right? And the negative publicity would hurt him. And so people who do this sort of stuff for a living, there are analysts and people who do these sorts of decision-making uh, scenarios for a living, they have to weigh the financial consequences of these two. Okay. Very often, companies know that they're not meeting their standards, but they decide that they are making so much money, it's not worth correcting. A classic example is the Ford Mustang. Right back in the 60s and 70s, they knew, for example, that the mortality rate was higher than it should be because the car was unsafe. But they had people who did calculations and figured out they're making so much money from the design of the car that it's cheaper to settle a few lawsuits from wrongful death than it is to go back and redesign it. So the calculus of how people make decisions in business, it has ethical implications. You have to think about, well, not only, is this financially the right decision, but also, is this morally the right decision too? Okay, the last sort of thing that can occur when you're doing hypothesis tests, the last sort of error that people fall into is what I call errors of practical significance. And so here's kind of an example. The military collects a lot of data on soldiers because they have to make boots and they have to figure out how many boots to make and suits and stuff like that, right? And so suppose it's known that the average height of a private in the U.S. Army is 5 feet 8 inches. And we do a hypothesis test and we find out that, the sample average is 5 feet 8.01 inches. Do we really care? Well, the answer is no. Okay. But the point is this. If you run a hypothesis test with a large enough sample, okay, you're always going to reject the null. So let me just kind of illustrate what I mean. So if the null hypothesis is true, the average height is 5 feet 8 inches. And the central limit theorem tells us that sample averages we get have this normal distribution. And suppose we get a sample average of 5 feet 8.01 inches, okay? So we get a value that's close but a little off. The point here is that if we choose a large enough sample size, okay, what's going to happen is this 3 standard deviation window is eventually going to get so small, okay, if I choose a large enough sample size, I can make that 3 standard deviation window so small that I will reject the null, even if the sample estimate's really, really close, because this 3 standard deviation window is going to 0, basically. Now, why is this important? One of the things that throws people off a lot is they use really large data sets, and then they reject the null. But they're confused because the sample estimate is really close to the value under the null hypothesis. And what you have to understand is that your sample can actually be too large. If your sample is large enough, you'll always reject the null. So you have to be careful when you read these studies where people say, scientists have proven this isn't true. Well, first of all, you can't prove anything with data, but they're meaning that they rejected the null, okay? But if their sample is large enough, they're always going to reject the null. In other words, if my sample is large enough, I'm always going to reject the null hypothesis that says the null is 5 feet 8 inches. Because the reality is that it's not exactly 5 feet 8 inches. It's a little bit different, but we don't care about that small difference. Okay. But I'm going to be able to resolve that or detect that difference if I make my sample size large enough. So this issue used to not be so much an issue when I was a student, but however, now with big data, it's a huge issue. You could run a hypothesis test to see if your sales have changed, come back and tell your boss, yeah, sales have changed. And you go ahead and you implement some sort of policy, right? Going back to this table here, right? You could say, oh yeah, there's been a difference when there really isn't. Your company puts all this money into this belief, okay, for nothing. They waste money. Whereas your competitor is smarter. They realize that the sample size was too large and there's not a real difference, and they don't make the change, and they have that capital, and now they have a competitive edge over you. So these are things to think about when you're running hypothesis tests, especially with very large data sets, and some of you may in fact be doing that. Okay, in the next video we're going to actually start working some hypothesis tests.